Hello. Today I'm going to explain my code and my solution for the homework 1 exercise for the course Computer Organization and Architecture. So the goal of this exercise is to implement looping and conditional control flow without using branch instructions like B or B, I don't know, BLT or BGE, BGT. So without using any of those instructions, we have to implement a looping algorithm. So the thing we have to do, so let's say the thing I had to do in order to achieve it, was to modify the PC value directly. And actually, this is what branching does internally. So branching actually modifies the value of the PC so that it can go to other sequence of code, and so disrupting the sequential flow of the program. So the main objective of this exercise, or let's say code, was to implement that PC, let's say PC modifiement ourselves. So let's jump into the code and I will explain step by step what each line does. Okay, let's continue with our variable initialization. So I have my notes here. So R0 represents M. M is our starting point. From which number do we start counting from? So M is our starting point as requested in the exercise. So R0 represents M. And then we have, and R0 will act as a counter. So what I mean by counter, it will get incremented by 1 in each iteration of the loop, as I will explain it in this section of the code. And then we have R1, which corresponds to N, so it's the endpoint, let's say loop boundary. So after which number should we stop? Let's say summation. After which number should we terminate the loop? And then we have R2, which represents the sum, and it's the accumulator of the loop. So after the end of the loop, R2 is going to be equal to M plus 1 plus all the way to N, and both of them are included. And then we have R3, which is 4, and as my notes, I have written that 4 is number of bytes each ARM instruction takes. Yes. Okay, I explained why do I need constant 4. Yeah, because in ARM assembly, each instruction is 4 bytes, so each instruction takes this many of bytes. But why do I need, specifically, why do I need that? Why do I need R3? Because I don't have, as the requirement of this exercise, I can't use any branches. So I have to manually calculate the offset if I want to jump certain number of instructions ahead or backwards. So if I want to jump certain number of instructions forward or backwards, doesn't matter. I have to calculate that offset in bytes by myself. That's why I have this register to help me with that. Because let's say I want to go back 5 instructions. I want to go back 5 instructions backwards. I can't just write, but I have to account for the size of the instructions as well. So that is where R3 comes from. And I'm going to explain R6 and R4 in depth in the next section, which I'm going to, not in next section, but I'm going to explain this more in depth in the later stages of this video. So alright, let's explain the loop body logic here. So this is our loop body logic. And so line by line, this is adding R2 plus R0 and storing it in R2. Yeah, this is for our sum variable in order to have the correct sum at the end of this loop. And then we increment R0 by 1, so this increments our loop counter by 1. So R2, so essentially this happens. R2 is equal to, let's say more shortly, R plus equals to R0. Okay, right. So, and R0, this is even simpler, plus plus. So this two lines essentially do this. And then we have CMP. So compare function does this. So it subtracts R1 from R0. R1 from R0. So this is R1, R0 minus R1. This subtracts R1 from R0 internally, and it does not store the result, as we know, and it updates N's and Z and CV flags, which with the help of these flags, we will use conditional executions like I did here. So I will explain this later on. So this CMP updates the N's and CV flags and does not store the result. It only updates the condition flags. These flags are then used for conditional execution. Yeah, that's it. That's it for the core loop logic. Again, it's just adding R2 plus equals to R0, incrementing R0, and making sure whether our loop should be terminated or not. So now I want to explain the most crucial part of this code. The most crucial part of the code is this. Why it is so important is that this piece of code, this instruction, allows me to go back to the beginning of the loop, which is here. So this allows me to go here, and I'm going to explain how it does it. How does it help me to reach to the beginning of the loop again? So first of all, this is a conditional execution. So LE sub LE means that this instruction will going to get executed only if R0 is less than or equal to R1. So R0 is less than or equal to R1. This is the only way for this instruction to get executed. And the crucial architecture detail here, so the crucial detail here is that PC value here. Why? Because PC value is relative to this instruction. It's not relative to the whole program. It is relative to this instruction. And the tricky part is that the PC does not equal the PC is not equal to the address of this instruction. It is actually in ARM assembly. In ARM assembly, the PC actually points to 2 instructions ahead. So PC is address of current instruction plus 8. Well, you might ask, why plus 8? It's because of the pipelining, because in ARM assembly we have 3-stage pipelining. And what is that 3-stage pipelining? Is that it is while this instruction is being executed, the next instruction is being, so while the, let's write it, while the current instruction is being executed, the next instruction is being decoded, the following instruction is being fetched, and PC points to the instruction that is being fetched. So that's why it points 2 instructions ahead. So PC actually points 2 instructions ahead. So you might ask, why not plus 2 but plus 8? But as I said, number of bytes each ARM instruction takes is 4, so it is not plus 2, it is plus 8. That is why, so in this, when the PC, when the, let's say, CPU is executing this code, PC actually points 2 instructions ahead. And this thing, let's say this concept is directly related to these guys. So it's directly related to these registers. So why? So in this, so what I am doing here is that if R0 is less than or equal to R1, I am subtracting PC. I am subtracting R4 from PC and storing it inside R5. And what is R4? R4 is R3, which is number of instructions, times R6. And R6 is 5. So that will make R0 equal to 20. Okay, 20. And why 20? It's because let's count it. I mean, we can. So what is our objective? Our objective is to go back to the beginning of the loop. So let's count how many instructions is this instructions ahead of this of the beginning of the loop. So if we count, there are actually 3 instructions, 3, but we do 5 here, and this 5 is actually for the pipelining. As I said earlier, PC always points let's say PC points 2 instructions ahead. Therefore, when we write our code, so when I was writing this code, this was the most trickiest part, because going by 3 instructions was not landing me in the correct destination. So I had to account for the pipeline offset, which is 5. So that is why R6 is equal to 5. R4, that is why R4 is equal to 20. And during this, if R0 is less than or equal to R1, I do PC minus R4. So this is actually the offset is becoming, so we can think that, okay, R5 is equal to current address plus 8. Plus 8 is because of the pipelining offset, minus 20. So it actually helps us to land at current address minus 12. So it actually helps us to land at that address. So this lands at, so because of the 12, we are correctly landing at the start of the loop, which is here. So now let's explain the greater than path here. So we explained what would happen if R1 is less than or equal to if R0 is less than or equal to R1. But in the case of this loop, because we increment R0 by 1, there will be a case where R0 is more than R1. And in this, when this condition holds, we want to terminate the loop. That is why, so we have this piece of code. So let's examine this. So what happens? So this code executes only if this condition holds. So if this condition holds, this piece of code is going to get executed. And this code is, the purpose of this line is to terminate the loop. So this is so this condition means that loop should finish, and this ensures that, okay, loop is going to get finished. Loop is going to get terminated. So if greater than, I do R5. So I do R5 PC if greater than. So again, let's remember that PC is what? PC is, again, PC is this current address plus 8. So again, PC is, sorry, PC is current instruction address, let's say instruction address being more specific here, so plus 8. So now R5, so if I do R5 is equal to PC, R5 contains the forward execution address. So R5 contains the forward execution address. Then we execute, then we come here and execute this. Then we come here, we execute this. So let's say R5 is contains a forward execution address, as I said, and then after all these are over, we are coming to this. This is the core of our exercise, the core of our code. So if LA was true, so if R0 is less than or equal to R1, R5 will contain this. So we're going to go back to this. But so we're going to go back to this. But otherwise, if R0 is more than R1, if R0 is more than R1, in greater than case, R5 contains the forward PC. So forward PC means that we will continue the execution, we will not go back to the start of the loop. So in greater than case, execution falls through here. And why here? Because we said PC is current instruction plus 8, which is PC points 2 instructions ahead. And if we say R5 is equal to PC, then it means that, if we do R5 is equal to PC, we are essentially landing in this piece of code. So because if we go here, so PC would point to here, and if I do move PC R5, so move whatever value we have in R5 to PC, we will land in here. So which terminates the program. So this is essentially my code. I explained it line by line, so part by part, every section, every reasoning behind it, and we can also, and let's go to the simulation part. Okay, all right, so let's continue with the simulation part. So let's refresh the page for registers to be, yeah. So this is my code. Let's say compile and load. So we start from variable initializations. So R0 is 0, R1 is 5, R2 is 0, and we want R2 to be equal to F in hexadecimal, or let's say 15, because numbers, so because 1 plus 2 plus 3 plus 4 plus 5 is equal to 15. So, or this is equal to this guy, F. Let's say F. So at the end we should see that R2 is F. So okay, so the first start of the loop is that R2 is equal to R2 plus R0, because we start from 0. R2 is going to be 0. Incrementing R0, which is going to 1. So comparing, so it updated NZCV flag, and means that, okay, less than or equal to, of course. So this piece of code will work. And move PC R5, and R5 is points to 18. So if I execute this instruction, it will go to this instruction, which is the desired outcome. So we went back to the start of the loop. So if we do this, as you can see, okay, A, so when R0 is 4, yeah, we get A because A is equal to 10. Yeah. So this is the last iteration. F, yeah, we got an F, so which is the desired outcome again. And then this will work. So PC is 28, R5. Yeah, R5 is 30. And move PC R5. So we landed in SVC. So the code we're going to get terminated. So that's it for my explanation. And yeah, thank you for your attention.